of University of Birmingham's IEEE student branch. And today we'll be having a distinguished lecture, and I'm going to hand it over to Professor Xiaoping to welcome our speaker and kick us off. Just a few logistics before we do that. All the questions today will be done through the chat function. So if you've noticed, everyone's been muted. So if you have questions for the speaker, go ahead and pop those into the chat as we're going along. And then at the end, we should have a nice robust question and answer discussion. As well, this meeting is being recorded. So just wanted to inform you all of that before we get started. Great, so now I'll hand it over to Professor Xiaoping.
Good afternoon, ladies and gentlemen. My name is Xiaoping Zhang, Professor of Electric Power System at Birmingham University. It's my great pleasure to welcome our speaker, Professor Bikash Pal from Imperial College London. He is a very distinguished expert in power system control in the world. Also, I welcome all the participants to take the time to join this webinar today. In fact, Professor Pal and myself got to know each other many years ago, and subsequently, we published a book together on facts. Today, we are very delighted to have such an exciting opportunity to host this IEEE Distinguished Lecture webinar. Finally, I appreciate the excellent works of Daniel and Jianing, IEEE Birmingham student branch. Also, IEEE UK and Ireland chapter to make this seminar happen. Wish all of you have a very good time today. Stay safe and healthy. Thank you very much.
Great, thank you, Professor. So as Professor Xiaoping has informed us, today's speaker is Professor Bikash Pal from the Imperial College London, here to give us an exciting talk on dynamic estimation and control of power systems. So with that, we will hand over the presentation to Professor Pal and look forward to the discussion.
Screen, see the screen now?
Not yet. Now we should be able to see it.
Okay. First of all, thank you very much, Daniel Jianing, for organizing this, and most importantly, Xiaoping. He is very modest, but he is more than a very good friend of mine. If you want to know that way, we wrote this book in 2003 together, but I only contributed 2 chapters, and all the other 7, 8 chapters, it was from him. And then he took this effort to translate this into Chinese, and it was a huge success in China. That's what I heard. But only my grievance remained with him is that he kept all the money of royalty from Chinese sale. I did not receive anything. No, I'm just kidding. So that was a very good book. And Xiaoping, he himself is, a fantastic researcher in 3-phase and including the facts, how you include the facts device into power flow formulations. Very good work. And that's how we work together. Now let me see this one here. Yes, now laser pointer, and then this. Are you able to hear the full screen now?
Yes, yes, we can see the full screen.
Okay, so this one, then I go on with this. 1 second. Let me bring my keyboard close to me. Sorry about that. Yes. The transition to low carbon generation, has led to many challenges as well as opportunity in terms of, system inertia reductions and uncertainty into the system characteristics. So that way, ineffectiveness in the control procedures that we have been following for years. So essentially, it is a very difficult regime in power system dynamics that we are moving through, where we now feel that more and more measurement based and identification based control and estimations are going to be more important and necessary than the pure model based approach, which normally we do on the planning model. Why we need to do these dynamic state estimations? The states which describes, okay, let me move this here. States which describes oscillator dynamics of systems such as angles, speed, fluxes, voltages, they could be estimated dynamically if you know the relations between them. And then these dynamic states can be used to design controller for power plants and fact device such as STATCOM and thyristor control series capacitors. That's what Xiaoping has done a lot of work on. Can be used for system control and protection following a small and large disturbance. So this is this, and typically this is how the network frequency change when there is a drop in generation or increase in demand. Initially what you see is system is frequency is contained by the inertia, is the frequency containment reserve, and then the first primary frequency response here, and then secondary frequency response. And these, what we do that means the system states are changing, the control has to follow that, or guide those changes to a most acceptable stable equilibrium. So this is around this time normally the droop works, droop control here, and then in the secondary, then you need to have more fuel etc coming in, that automatic governor AGC control, load frequency and AGC. This is the LFC region, this is the droop, and this is the inertia. And then you have a tertiary, not every country has that. So estimation model should be detailed enough to consider all these factors which affect the states during the transient period. This is the transition period. The time delay for estimating the states should be as low as possible. Then only you would be able to quickly act, because these controls are very time critical. But if we want to do it centrally, the update rates of the communication networks used in present day power systems are not fast enough. And there are real-time knowledge of system-wide model and operating conditions required, and then there are issues with the communication packet dropouts and delays, disordering, and cyber security threats, etc., etc. So then the alternative would be a decentralization. So decentralization is the most logical alternative to centralized estimation, as control as it effectively eliminates each one of its challenges. And how to decentralize when each component of power systems is strongly coupled to the rest of the system? It is difficult. For example, all generation units or electrical machines are coupled to each other to the with the rest of the network through its power flow, the voltage, current, and their angles. Typically, that can be expressed as nonlinear differential equations, and also there would be some output equations. There could also be some algebraic equations, because the stator transients normally 50 Hz. We treat them very fast with respect to electromechanical dynamic time scale. They can be assumed to be that way, algebraic. So you have essentially a phasor representations, dynamic phasor of those state variables. So typically, what are those state variables? Those state variables are like angles, speed, flux, transient voltages, and excitation system voltages. And the input is reference input of the excitation systems. What we do in decentralization, we introduce a concept called pseudo input. What is the pseudo input? It is the terminal voltage and its phase angle of the generator. We treat this as an input, and also we treat the output current of the generator and its phase as measurement, so or output. So now with the rest of the network, this generator is connected through its voltage, magnitude and angle, and current injection and angle. Now if these two pair of voltage vectors and current vectors, we treat one as input, another as output. So by that we can decouple this particular generator from the rest of the whole systems through this input output pair. So that is the whole idea about pseudo input and decentralization. Usually there would be noise of certain statistical characteristics, so that the pseudo input would be the actual minus the noise, or the measured minus the noise, and measured theta minus the noise. So these are all the actual pseudo input. This makes the estimation and control for one unit completely independent of the other unit. So essentially what you are doing, you are mathematically decoupling it, but not physically. Physically they are connected with the rest of the systems through this voltage, angle, current and phi. Now how then you could say or justify that whenever there is a change in the rest of the network, how that change, impact of that change would be reflected in this generator state variables. Typically if there is a change in the demand, every generator contribute to that, so that means there will be change in the machine load angle and also the excitation systems output, etc., etc. So how those changes would be then reflected if we decouple. So as you know, the node voltage and current phasors that we have gone with as input and output are algebraic electromagnetic quantities. Any change or disturbance in the system is instantaneously reflected in voltage and current phasors of all the nodes in the system. Because these electromagnetic quantities, the speed is in electromagnetic transient regime, and we are talking about electromechanical, which is about a 2 Hz. So within that time scale difference, any change in the network, typically if there is a fault, what we normally do in simulation, we immediately adjust the algebraic variable, the currents and their angles, voltage and their angle of the network. So that means that change automatically is taking place, and that would be reflected on the change in the V and theta and I and phi. So that's how the generator will see that change. So by decoupling the systems equations and by treating one pair of as input and another as measurement, we can then proceed with the decoupled estimation without losing any information from the network impact. Now that we then this decoupled generator estimation we could now do through unscented Kalman filter, and we call that as a dynamic state estimation. It is completely decentralized. It is completely on the basis of the locally available parameters and measurements, and it provides all the dynamic state of the machines in real time. So this is how we do in unscented Kalman filter. What we do, we avoid the expensive linearizations of the nonlinear equations and updating the Jacobian by having a sigma points, set of sigma points we generate, and thus the nonlinearity of the state equations is preserved and cost linearization is avoided. This V, W, theta W are assumed to be white noise and are treated as states in the filtering equations. Current and phi are treated as normal measurements. Let's see this. So how we generate the sigma point? We generate about n sigma point upper half. This is each of them. This is xi hat k minus 1 means previous estimate of the state, whatever state vector that you had at the this thing, the ith generator. This is all set. Ni pxi ki. This is a in the lth here. The L is equal to 1 to up to this, so it can be 1. So pxi, and then this, take the square root of that. So that would still be a column vector. Pxi ki, k minus 1 is a column vector because this is the ith say machine we are talking about, and this is the all whole sets, a column multiplied by ni. So that's a column vector. Take the square root, add with the previous estimate to generate the first half of the sigma point, and then subtract from this to get the second half of the sigma point from 1 plus ni to 2ni. So the xil is the lth sigma point for the ith generating unit, right? Now this is the lth column of this, which is found by Cholesky factorization. Fine. Xi is state vector of the ith unit, and Xi is its estimated mean. So how you do then? So Xi hat is the estimated mean. Pxi is covariance, and the number of elements is in it is Ni. So this is all clear. So what then we now do? We predict the state. What we do? We put all those sigma point with the pseudo input, and we get xil bar for L is equal to 1 to 2n for all now. Once we get that predicted value, so this is around the grid of the sigma, we take the mean of this to get the predicted, the state prediction on, and then this Pxi become covariance of xil hat plus process noise. This you could generate xil hat column times the xil hat transpose, that gives you the covariance. But these are all in predicted, they are not still corrected. Similarly, you do the prediction for the measurement. Gamma IL is HXIL because the measurement, the output, that current and phi is function of the state and the pseudo input, voltage and current, voltage and angle. That one you do for all L 1 to 2n. And once you get that, then take the mean of that, that gives you yi hat minus. This is the predicted mean of the output. And then this is also the predicted, the covariance, PYI covariance of YIL plus the measurement noise. And now what is PXI? So you take that XI, XIL hat process noise times the YIL hat. So that gives you the cross covariance of XIL minus and YIL minus. Okay. So this is the cross covariance, this is the measurement covariance, and the Pxi is the state covariance. Once you get all this quantity plus this mean of the prediction, then you can have a Kalman update. Kalman update is a Kalman gain, the cross covariance times the measurement covariance inverse, that gives you the Kalman update, and then the state corrections. Xi hat, the ith now is xi minus this, that is that you have done on the basis of the sigma prediction. Then the Kalman gain adjustment k times y that you have measured and y that you have predicted. So these two error. The job of the Kalman gain is to drive this error to 0 so that eventually xi hat becomes your xi minus. And then once you get this, you then update the state covariance matrix Pxi by from this estimated, from the prediction to this minus k this. So these are the 4 steps of standard uncentered kernel filtering, and then we now need to treat the model of the measurement noise and process noise, and those things, as I said, they are white noise. But then the covariance, particularly, there should be 0 mean, but the covariance should follow certain threshold, and those threshold would be set by the normal sort of standard like IEEE C37 and then total vector error and so on. So from those standard, we will get the upper limit or threshold of those covariance of those error. We then apply this uncentered kernel filtering technique to a 68 bus benchmark systems. This is an IEEE PS the dynamic model network, and then we generate the measurements. That's how it all comes like this. After that, we do the estimations to make sure that our estimation is based on this measurement, and then we can add the errors and see the estimation of the accuracy with the error. So these are all the error that you see here is of the order of 10 to the power of -4. So these are all just to sanitize your algorithms that it all works and it provides you the estimated state from the simulations, which is black on completely on model parameters, and then add the noise, do the uncentered kernel filtering and plot them. So this is how you get. Now the advantage of the decentralized algorithms, if you do it for every machines, it will have its own local processor. So that complexity or scalability is as many number of dynamical equations that you have and state that you have in that particular generator. Normally that, will remain around 10 or 15 for every generator. That means processor only had to deal with 10 to 15 sort of states. So if you move on from IEEE 30 bus, 68 bus to 145 bus, the number of generators increases, but because we are doing decentrally, we are doing all simultaneously, so the time doesn't change. Whereas for centralized one, this time is changing. You see that from 30 bus to 145 bus, when the network is almost 5 times larger, and what you see that the time requirement to estimate is almost 100 times. So this is how the decentralized algorithms helps over its centralized counterpart. Now I need to talk about the practicality of PMU based Dharmic state estimator. Now PMU rely on GPS synchronization. GPS are susceptible to atmospheric effect, clock errors, and multipath effects. So there are also sometimes, the issue of cyber securities. So poor accuracy for standard PMU noise and so on. And then also when you are doing this PMU based measurement, you are getting this PMU measurements at every location, and not necessarily all the PMUs will be supplied by the same vendors. So different vendors will have different class of errors. So that way you will have these latency, sampling, etc. So those, the practicality of PMU then introduce some kind of inaccuracy in the estimated state. So that is the impact. Now how we can find an alternative to PMU based DAC? So what we could do through GPS synchronization, PMU just provide a common reference frame for obtaining voltage current phasors, and these phasors are required for DAC. Like we need to have a reference phasor, because we are doing delta, we are doing theta in every generators. So that delta has to be with respect to a reference phase that has to come from a central location. So that is where actually is the difficulty or the probability of getting the errors and inaccuracies. So what do we then do? We rely on GPS synchronizations just for timing pulse, and we can remove the requirement of common reference frame in the estimated model. How we could do that? This we can do like this. Remember, we got theta, that is pseudo input. We also got delta, which was load angle. Now if we take, rather than delta and theta as two separate these variables, one of them is state variable, another is input. If we take the difference delta minus theta, so the common reference angle that was to be that was needed for delta and common reference angle that was needed for theta, they are here, they are now cancelled. So now it's a relative angle, so alpha does not require the reference frame. So that means PMU does not have to, you don't need to receive actually a common reference angle through communication. The dynamic equation is now alpha dot is equal to omega minus f, right, rather than just omega minus d theta dt. So rest of the states and dynamic equation remain same as PMU based DAC. The frequency is used instead of theta. The new pseudo input is now V and F, not V and theta. This then delta can be reconstructed if we know the reference angle. Now we also talk about the robustifying the uncentered kernel filter. Now uncentered kernel filter has those covariance and all those the properties. We have seen that X transpose, X column into X transpose, Y column into Y transpose, and then X column into Y as the cross covariance. Now there actually we define a limit, and then it works on that basis. And as the sample number moves, in normal uncentered kernel filter, we always keep the threshold fixed. Whereas what we need to do is we need to make sure that in every iteration, when it is getting actually the samples, along with the samples, we also provide the statistical property of those samples, which would vary from sample to sample. Rather than for remaining, the fixed for the whole process, we just provide the sample measurements, and along with the measurements, we also provide its statistical property. How we do that? We get the raw signal from the current transformer, voltage transformer, that is discretized, and then we pass it through an interpolating discrete Fourier transform, which then produces those magnitude, the estimate of this quantity and their covariance. So every time then it gets a new covariance. So the state that you obtain, it always become more accurate. So analog signals of voltage current from CTVT are sampled at a very high rate. This stage, frequency, theta and magnitude calculated as parameters of the analog signal samples, yk using interpolated discrete this. Then at the uncentered Kalman filtering stage, estimated mean and variance of these parameters are used to find estimates of state using uncentered UK. So these are all the details about this, this magnitude of this, and then these are all the detail about their the covariance at that sample. So this is how you can see that it depends on the number of samples and also sampling frequency and so on. So in other words, what we get is this UKF gets the frequency and magnitude and sigma f square and also sigma ym square frequency. What is the magnitude? Magnitude is the voltage magnitude. Frequency is the frequency. That is the pseudo input. So it will have two, magnitude and then two covariance obtained from analog and are given to the input second stage. These 4 steps in uncentered Kalman filter are applied to recursively obtain final estimate. So what is, because of constant updation of variances of V and I, the obtained estimate remain accurate for varying operating scenarios. Another reasons behind robustness besides removal of the reference frame. So this is how you see this. Simulated is red, DAC with 1% total vector error in measurement is blue, and then robust DAC with out PMU and 3% error in the measurements. When you are not measuring through PMU but you are measuring through normal CTVT, the error band is high or something like this, normal measurement. So this is this. But you see that with the robust DAC, the black is following more close to the red, or the green, the blue has got so much of noise. For 3 state, speed, state, quadrature axis tangent voltage, that is speed voltage in the tangent domain, and alpha 1,3, that is the delta minus theta. So we also, this result of the robustness, this is DAC with 3%. You see the blue is this robust DAC without PMU and 1% error in measurement. That is the black dash, which is even more closely following the simulated value. Now these are all the errors you could see for these state vectors here. This is the error for PMU based 1% TVE. You see that they are 10 to the power of 3, 10 to the power of 4, only they are 10 to the power of 3. Whereas when you go for that IDKFT pre-filtering with 3% measurement error, you see that your error accuracy of the estimate is even better with 10 to the power of 4, 10 to the power of 5, and then 10 to the power of 4. So it's always one order less, 1/10 less than its the middle column. So benefits is this: it's a free robust estimation method which takes care of all the changes taking place in the systems, local CTVT measurements, not affected by the GPS or non-standard accuracy, dual stage estimation method, filter noise, harmonics, bad data, and improves results with each new measurement. Estimation process remains valid for any state operation, steady state operation or transient operation. Estimation time delay is also very small. Now I move to the control. In the control, the basics of power system oscillatory stability, we know this is electromechanical instability. Normally, this is the mode. If they are moving along this line, there is a damping and there is a frequency. If they are moving along this line in the S plane, that means this is completely oscillatory unstable. It always does like that. This one, it does like this sort of damping. So to ensure the stability and any oscillations in the system must have the poles in the closed loop inside this sector. This eigenvalue which contribute to the power system oscillations are the electromechanical mode. We talked about this. In a centralized framework, dynamic estimation control, remote signals from all over the world need to be brought to a central location. But centralized framework is not very practical because of the measurement updates, data loss, time delay, cyber security threats. complete system model needs to be known. That's there. Whereas in decentralization, the most logical solution to the problem of this centralized estimation and control, as it essentially eliminates most of this problem. So PMU is getting its clock signal from the satellite, and that's it. And that is now tagging to this local measurement, and then local measurement, local estimation, everything is happening locally without getting the global reference frame angle. Control design should ensure good oscillatory stability, and we need to then do optimal control law that would minimize the control effort. And also linear optimal control theory can be used for small disturbance. Linear quadratic regulator, I mean, we have done a lot of things on H infinity, H2 norm, and so on, LMI, etc. Now, linear quadratic regulator cannot be used directly here, as pseudo inputs are present in decentralized equations. Linear quadratic regulator cannot be done because LQR, it only assume that you have x dot equal to ax plus bu form, linearized bu form. But in this case, there is an additional input has come in that we have defined it to be pseudo input. That was the requirement, that if we define it that way, then we could decouple the machine from the rest of the network physically. And optimal control law, then that is naturally for LQR with the pseudo input, and optimal control law needs to be formulated. And that's what is done. This is your state. This is this xi hat. This is the state matrix. This is the regular input. You could stop here without bothering about this. Then you can easily go with an LQG. But once you bring BI, UKI, so then the total quadratic cost after incorporating cost associated with the pseudo input is, this is the J. K is equal to 0 to n-1, xk transpose qxk. This is the control cost optimization. This is the this is the control cost optimization. This is the state cost optimization, and this is the pseudo input cost optimization. And we find a control law like this: uik is fi xik plus gi uik. What is this gi uik? Gi uik, this is the contribution from the pseudo input, and this is the state. So that's the impact of the decoupling that you are now incorporating into this. And these are all the matrix, the F matrix, which is part of this, the weight, control weight, and then also the input here, state matrix. These P's are the normally the solution of the Riccati equation P and that. And this GI is that one that you see here is coming from the pseudo input. Is Fi A Pi Pi minus Qi this. So that's the control law. We could extend this. We could then call this as extended linear quality, because up to this is quadratic regulator Axk Buk, Cxk Duk, but this one is additional. This one is additional. So that's why we call as an extended LQR, and we have treated that. Now, damping control in conic section, in that X plane, would corresponds to a specified damping maps to a logarithmic spiral in Z plane. Normally, the whole of the left half plane of the S plane is a circle in Z plane. Inside the circle, you are positive. Outside the circle, you are negative, or something like that, right? So on the circle, you are conditionally stable. Confining closed loop poles with a spiral is not practical. So spiral can be then approximated with the disk of radius r and center beta 0. This substitution of disk should be tangential to the spiral, because it has to be there. Then only at the tangential point you get the minimum frequency and the minimum damping ratio. So where in Fm is the frequency of the electromechanical pole, and Dmin is the desired minimum damping. The optimal control law for confining closed loop poles inside this disk remain as ELQR, except that A, B, B prime are replaced by A minus beta I, and by R, B by R, B prime by R, because we have a radius of R of the disk and center of beta. If radius is, say 0, then this is something different. But if is the beta is 0, so here you are coming to that same A, where beta is 0. Now that's the this is what I would say, that this is the spiral like this, and then how do you get the disk? The disk is this damping ratio. This is the disk. Here they would be tangent, and then you do this. Complete methodology then, decentralized DAC provides dynamic states at the operating point. Decoupled equations of a machines with pseudo inputs are discretized and linearized at the operating point using the dynamic state estimate. Parameters R and beta found for the substituting circle after finding the machine's electromechanical poles. Once you know your mode, the frequency particularly, then that would help you to find your R and beta, and then you can get the closed loop damping by this design of the disk. So ELQR control gains calculated after incorporating R and beta multiplied with states and pseudo inputs, and the resulting control applied to local AVR. So that's coming in because that we saw that X transpose, we had QX, and then U transpose RU, and then U prime transpose R prime. So those things, that equation, that is the equation we are trying to optimize, and in that process we get F matrix for our pseudo input control part, and also the normal gain matrix for the state control gain matrix. So this is how, where you see this is the machines, this is the PMU. It gets the clock signal only, and then all the terminal voltage and current that it gets from the local CTPT, it goes over here, and also it goes over there. Extended LQR controller design must have actually these input, and then what we do the dynamic state estimation here, and in that itself we apply the IDFT and we estimate the local state, and then we apply the control with this pseudo input and B prime etc., and we get VSS1, which is now going to the excitation system voltage regulators reference input. That then modulate the EFD, which is the field flux voltage or excitation, and then this excitation, change in the excitation produces a electromagnetic torque, which is counteracting the oscillations. So that's how it's dampening this. Similarly for the generator 2 and all up to generator 9. So now you see that everything is decoupled, and each of these generators are connected to the transmission network and loads just through this line, one line. That is, it is injecting current at an angle, and it is treating its voltage and theta as its input. So this is how the whole the DAC based ELQR design goes. We apply that in the same systems with this thyristor control series capacitor in one of the line between the two area, and then we see that with this extended LQR we get this black, and with the PSS, normal PSS, we get this blue. Now when we do that, we need to make sure that the PSS, the amount of energy or control cost associated with the PSS, has to be comparable with the control cost with ELQR. We could always have a much damped response with a much powerful controller ELQR, and then we could always compare that with poor sort of control where we have an oscillatory control, but they did not provide enough control energy. So this is how you then optimize your energy requirement, control effort requirement. That is where is the effectiveness of ELQR. We also do something with the centralized, the wide area damping control, and also decentralized ELQR control. And what you could see here is there is this, the blue is centralized, and then the decentralized is that solid line, and then that is how they behave. Now we do the modal analysis. For all, open loop had so many mode, about 4 mode up to 79 Hz. With extended LQR, the frequency is brought down, damping is extremely increased to 20% for one particular mode, and with PSS it was 14.8, with wide area damping it is 70.8. This is for one frequency we call mode 1. Similarly, that network has got 4 critical mode. Similarly, you see that the dampings are improved by every method. Frequency is not changed a lot. Why you don't need to change the frequency? Because you must not be playing with the synchronizing torque. Synchronizing torque is the the quantity that need to be focused during the transient stability stage. We are talking about post-transient. This transient stability stage has been guaranteed by the generator. Machine has survived, and now we are coming back to a post-fault equilibrium, which is now oscillatory. And at that time, how we are damping this oscillation. So this is the whole idea. Now the cost, if you think total cost, state cost, that is X transpose QX, and then control cost U transpose RU. So this is for extended LQR. This cost is 1.4, 1.8, 2.46, 1.15, 0.08, 0.18. This is for different operating conditions. 700 megawatt between generator of the area 1 to the generator of the area 2. New England power systems to the New England test systems. Similarly, 100 megawatt drop in the export. 900 megawatt increase in the export. 700 megawatt between these two line, and so on. So there you see that the total cost for the extended LQR control is always less. So what it is doing, this is the state cost, this is the control cost. And now you see that state cost here for PSS is more, even for wide area is more, whereas control cost is also more, 0.28, 0.13. So like that, if you see these figures from 1.4 to 0.08, and here it is 1.87 to 0.12, that is this, and then in this case 2.15 is essentially from 0.15. So this is the range. So that is, this range is bigger, this range is bigger, this range is smaller, and also the control cost here is small. So that justifies the robustness issue compared to these methods and so on. So there are some limitations with the linear control because they are only effective for small disturbance, so small sequence stability. Now, no mathematical proof or guarantee for global asymptotic stability, because this is around that you have linearized the systems and then you are examining it. So no mathematical proof or guarantee for global asymptotic stability, as only local modes are observed and controlled, more or less works like an adaptive and intelligent PSS which adapts with the time to system operating state. The one possible solution is decentralized nonlinear control rather than linear control. And how we do that? There are two ways to do it. One is energy functions, Lyapunov, another could be feedback linearizations. Advantage with this feedback linearizations and normal form is Lyapunov based method is that a general technique does not exist for finding a Lyapunov functions, while steps for finding a normal forms are well established. Moreover, a normal form is either fully or partially linear. Linear control techniques can then be used. So this is how linearized dynamics and controller expression LQR, looking at this, you could come with some numbers representing, this delta domain diagram in terms of states and so on. So then you see that for that asymptotic stability, the state which do not appear in the external dynamics describe the internal dynamics of the state. Fine. So they are the state which are not reachable or detectable. But as long as that both the internal and external dynamics remain stable under the nonlinear control, in order to show stability of power systems, global asymptotic stability is rigorously established by the following theorem. The internal dynamics of a power systems will remain asymptotically stable if the external dynamics of all machines in systems are asymptotically stable. So there is this. So if the external dynamics are stable, the internal dynamics will remain stable. External dynamics you are able to capture through output measurements. So this is the observability. So as long as the system is observable and controllable, then it is fine. But in that case, when it is controllable means all the states are controllable and all the states are observable. Some cases, some of the states may not be observable and some of the states may not be reachable. So that means we need to relax the stability requirement from asymptotic stability, observability, controllability to reachability and stabilizability. So this is what he is talking about. As long as your system is reachable and stabilizable, so asymptotic stability can be guaranteed through the nonlinear control with this with only those observable modes. So results for small signal stability, this PSS control extended LQR is blue, and nonlinear control is very fast. That you see that it is doing this. Now the amount of energy or control effort that would be necessary for nonlinear control would be much higher, but it actually makes sure that the state deviation is not much. So that way you can actually get this at much larger cost of control, effort of control. So this is robust for selective model. These are the open and the closed. For nonlinear control, you see the dampings are even much higher, 91%, 92%, 47%. Virtually it will not oscillate at all. That is what you see here. This black one, it is not at all oscillating. It's just, this response of delta 1,3 is like this. So this is how it has been very effective, but at the cost of a large sort of control effort. Results from the transient stability simulation now show you that the black one is the nonlinear control is much better. Whereas extended LQR and PSS, they are having this sort of very high frequency oscillatory sort of behavior. Now the critical clearing time, that means when the fault happens and how long you can allow the fault to go before the machine loses synchronism. For PSS control is 40, because they are all contributing to the synchronizing torque along with the damping torque. Extended LQR, you can wait up to 50 milliseconds, 10 milliseconds more. And for nonlinear control, you can wait up to 220 milliseconds. Because the nonlinear control does not let the system go out of, say, synchronizations or instability. Then nonlinear has a drawback. The control costs are almost 10 times higher. So, because you are doing it, you are damping, you are making the rotor speed damp very fast, means such a huge mass you are damping, means you need to have a huge amount of control energy. So that is the drawback with the nonlinear control. What one can do, it is best to use both linear and nonlinear as a combination. Like whenever there is a fault and fault is persisting, just switch on to the transient, the damping part of the controller. And once the fault is clear, then come back to the other one, that extended LQR. So that way, you could then for about 80 milliseconds, large energy goes, and then for the balance of the time, you can, stabilize the systems with low control effort. Now, all these things that I talked to you about, it is a work of 6 years, 3 years PhD and 3 years postdoc by this particular gentleman, Dr. Abhinav Singh, who is now assistant professor in University of Southampton, electrical department. So we came with a dynamic estimation and control of power systems in academic press in 2018. This was the book. After almost 15 years, I collaborated with Xiaoping, and we had a couple of editions, but we started in 2003 and then 2006 and Chinese edition. But this is on completely dynamic estimation and control of power systems. You get everything there in detail. I not only work in this particular topic, I have worked with many other topics, wind and solar. We are working on an ITN projects from European Union. These are the researchers. And then the black start scenario simulations through Kevin with a company where he is in internship, doing his internship. That's Deeptar Ghosh company, TNEI. And we got the other electric vehicles, and then this person is on microgrid protections, and Statis is on and this solar integration to the grid with hosting capacity improvement. Nicholas is working on again fault detections through frequency domain technique, and Firdos is working on distribution system volt and var optimization, which is also one of the DLP topic. I've been giving this to some places, and this particular person just left and became Royal Holloway College of Royal Holloway University, is now assistant professor. So that is the thing, and these are all the people who have been supporting me for my work since 2000, and that's it really. We have now time for question and answers. I stop sharing the screen, if you want, and then we could have this question and answer.
Great. Well, thank you so much, Professor. It looks like we have one question already in the chat from Dong Chen. So Dong has asked, do state-of-the-art power system dynamics, estimation, and stabilization take electromagnetic transient dynamics into consideration? For example, the charging processes of capacitances and inductances.
Yeah, it depends. In this case, we have focused on 1 to 2 hertz. By the way, I know Dong very well. He also worked in one of our collaborative projects in Strathclyde as a postdoc. Now, Dong, this one is for 1 to 2 hertz. So you could ignore the stator and electromagnetic transients. You stay on the electromechanical. Now, the DSC is a generic process. You could have completely on all differential equations. So when you go to the fast transients, particularly I know you are coming from the converters, interactions through network, and that interactions frequencies can go from few 10 hertz to even 30 hertz, 40 hertz subsynchronous. So at that point of time, we need to then completely move to the EMT type of model. That is what we do for subsynchronous resonance. So phasor representation is not possible, but you could always do full system differential equations and estimate each of the state. Then what would happen is in network at every node, your voltage and angle, they are also dynamic variable. So, and then what you do in this case, your pseudo input is an algebraic variables V and theta, and which you transform to V and frequency. And in that case, it will be your input, pseudo input would be a state itself, right? Not an algebraic variable. So that is this. So it can do for different frequency. Now there are a couple of more chat.
Yeah, looks like there's one from Ibrahim as well, asking about whether the simulations are carried out on a nonlinear model and how you guarantee CL stability when you use different controllers with switching.
Oh, all simulations are carried out on nonlinear model, yes. But the controllers are designed for ELQR on a linearized model, and nonlinear controller is also on feedback linearizations. So how do you guarantee CL stability when you use different controller with switching? Yeah, you have seen this waveform. There we created a large fault, and then you see that it was doing that, damping very well. So that was the asymptotic stability. You know, this the global asymptotic stability is guaranteed as long as the internal states are, you know, asymptotically stable. That there. Then this is Bayberries. What is the best method of setting the adaptive PSS control? Now there are many methods. We have done H2, we have done H in infinity, and also a lot of people have done pole placement. Many people have done just simple PI and so on. So there are also, I have done something on Kharitonov polynomial based design, and also the eigenvalue distance minimizations, and formulated this control as a second order cone program, that eigenvalue distance minimizations, making use of the relations of the shift of the eigenvalue with the residue expressions. So there are many. Again, Ibrahim, maybe it would be good to see the performance by comparing the results with robust MPC. Now I have not worked on the model predictive control, and you could you know, work on that. I have not done on model predictive control. This would give you an idea about the best that you can achieve from the systems. Yeah, of course it is. Yeah, but the MPC, you know, I'm too old to learn MPC. Next.
I think that's. I have one question as well while we're waiting for any others that might come in. I think in the beginning of your talk on dynamic state estimation, you mentioned the sensitivity to noise, and then showed how that affected both the different methods you demonstrated, and noted that the noise is based on the tolerances from some of those IEEE standards. Do you think that the current noise thresholds set out in those standards are sufficient to advance, you know, with kind of the increases in system performance that are necessary for the future, or do you see those standards as still being sufficient and really?
Yeah, in my opinion, they're quite conservative. 3%, 1% total vector error, 3%, you know, the measurement error. They are quite actually generous. And in future, more and more tools will come, like IDFT. I mentioned IDFT is an innovation in 2016. It came in signal processing, the method itself, and then we applied for the first time. So with more and more robust algorithms, which will be, you know, more tolerant to error, etc., it will be even better. It will be better.
Thank you.
That's from Daniel. And any other questions?
Great. Well, thank you so much for the wonderful presentation. If there's
Precisely
last
1
burning
hour.
question.
Precisely 1 hour, Daniel.
Yeah.
If I could borrow a minute or so, this IEEE election is going on for president and various division and region directors. And in 42 years of history, nobody from power energy societies, fought for this main IEEE presidency. So this time we have the past president Saifur Rahman, and also we have Bruno Mayer, who is for IEEE, as well as people who are past PS member from Region 8, Vincent Puri. So there are many people. And have you received this election email from the IEEE? How many of you have received and how many have not voted? Some of you may not receive because you have opted to send them to you by letter, and you have never been to your office because of this COVID, so you will never see the letter. So go to the website of the IEEE election and log in through your IEEE credential and please vote. And if you, yes. Oh yeah, oh, Professor Rahman is the candidate for 2021. Please visit the website below, and yeah. Great. So that's Jiang Li, welcome to the webinar of that one. So he did that. So I'm suggesting you to vote. Yeah, I mean, one of you have voted, but I know that all of you have voted or will be voting. I'm not coming to you for your vote. I'm coming to you to ask 8 or 10 people to vote also. You'll vote anyway.
I think there was a good discussion as well at the PS general meeting, kind of showing, I think Saifur Rahman gave a discussion there as well, and should be a good opportunity to get a good voter turnout.
Yeah, I mean, our society has got about 38,000 members. Some of them may not have the voting eligibility like student member, but whoever, about 30,000, but they have to vote. It's essentially challenge is to bring the people to the voting platform, not the voting. People to delete the email. So normally IEEE vote turns out, normally it is about 15 to 20%. Out of, right now there are, whole IEEE has got eligible voting member about 300,000 or 200,000 something, 274,000 people are eligible to vote. And in reality, you will see that altogether about 30 to 40,000 people will vote, and the rest, they do not simply care.
Great.
Yeah,
Well,
I could see
go ahead.
Panos. Is this Panos? Panos from Strathclyde. There is Pangatis Papadopoulos. I don't know who is this.
Hi, yes, this is me. This is Panos Bikash. Hi.
Yes.
Thank you for the talk. Thanks a lot.
Yeah. You are the Strathclyde rising star, right? This leadership fellow and all. Yeah,
Thanks for the kind words.
Much before Strathclyde spotted your star, I spotted long ago, right?
Indeed.
So what you have been doing it with Accept project.
Yeah, indeed. We worked for a while in that project.
Right.
Yeah.
Yes.
Thanks for that.
Okay. Anything else?
One last thing, we will be sending out, I'll post a link now as well. There's a link to a feedback survey as we're hosting this distinguished lecture program. Today, we'd love any feedback that you have about this event or future events that we may host. So I'd appreciate if you, just like voting, if you take a brief moment of your time to complete that, so that we can continue to enhance these events for the future.
Stu, we have this DLP program. They need this report, and in our governing board, we have the requirement. We meet twice a year on the governing board and twice for the executive committee, and in both cases, altogether 4 times a year, the chapter vice president chapter. Right now, the lady from Canada, Majan Armstrong, she usually present this to the president and all, how many events are organized, in how many people attended, in which regions. That way, every year we then set out the program for the next year, budget, etc. So if you say that, yes, we attended this, we need this type of more and more DLP program, not necessarily from me, there are many DLP speakers in the panel. More and more if you demand, then next year when you do set the budget for DLP, then more and more money will come for this. Right now DLP does not cost, it's all virtual, but in reality it will be all travel. I will be traveling to Australia, and DLP speaker from Chile will be traveling to UK, something like that. But we need to have more and more event. I have done, this is my last DLP out of about 8-9. I have been, this is not the last. There is one in September again in India. And this whole of last week, I was having DLP, sometimes 2 DLP, one in the morning, one in the afternoon, one in region 8, one in region 10, like this. But I really was looking forward to this DLP because it is our section, UKRI, and also lots of good friends, Xiaoping, and good to see Dong and Panos. Right, back to you guys if you want to say something, otherwise,
We just want to again, thank you for your wonderful presentation, and thanks to all of you for attending this DLP. And we look forward to seeing everyone at future events to come. So thank you so much, Professor Pal, and thanks for the discussion today.
Yeah, we'll do, and we'll meet sometime. When I come, normally I come to Birmingham and see my friend there, Xiaoping, maybe once in a year, once in 2 years. So next time, let us do this physically in
Definitely.
Yeah. So that way, I can get some good food also.
Oh yeah.
Yeah. So after this speech,
welcome you come back next time.
Yeah. Okay. Okay.
Great.
Thank you.
Well, thank you, everyone.
Yeah. Bye, guys.